space news from Roy Bryce. Then our main speaker for this evening is Dr. Luke Daly, whose presentation is entitled, Where Do Meteorites Come From? Our next Zoom webinar is on the 11th of January, which will be our astronomy fun quiz night, as well as a virtual party night. So bring along your nibbles and quiz for a fun night.
Whoever's coughing, could you mute yourself, please?
Right, so I'll pass over to Roy for the space news section.
Okay, thank you. I'll just find the right screen.
Right, I'll mute myself then.
Yeah, if everybody else could mute as well, that'd be polite, thanks. Okay, everybody see the screen okay?
Yep.
Thank you. Okay, so I was going to give a wee apology, but I think I've already done that. So let's just get straight into it. So the Extremely Large Telescope, which is ESO's new flagship telescope, has been built to answer the biggest questions in our universe. It's just received a 10% increase in its budget. The funding was approved by the ESO Council, and it brings the total cost of the project to 1.3 billion euros. The 39-meter telescope being erected in Cerro Amazonas near the ESO's Paranal Observatory in northern Chile will start operating later this decade. Robert, could you mute yourself, please? Robert McFetridge. Never mind. The funding boost will strengthen the scientific capabilities of the under construction.
Yep. You hear me?
Yeah, Robert, can you mute yourself, please? You're coughing and we can all hear it. Sorry. In 2014, the ESO Council gave the green light for the ELT construction, but stipulated that it should occur in 2 phases, with funding originally only committed for the fully working but less powerful phase 1. The revised budget includes the procurement of components originally deferred to the 2nd phase of the project, such as the telescope's 2nd prefocal station, 2 more laser guide star systems, a set of astronomy relevant atmospheric monitoring equipment, and a small technical building near the Amazonas to optimize operations and maintenance activities. The new budget incorporates the impact on cost and schedule of known technical risks and includes the cost of activities needed to bring the ELT into full operation as part of Paranal. You're probably aware China has been incredibly active in its space program during 2020. Launched on December the 10th, the Gravitational Wave High Energy Electromagnetic Counterpart All-Sky Monitor, that's some name, shortened to GCAM, represents one of the first new all-sky devices that will monitor fast radio bursts, high-energy neutrinos and magnetars. The craft is set to begin operations as soon as it enters orbit, and it's planned to operate for 3 years. To study these events, GCAM consists of 2 satellites, each weighing 160 kilos, that will orbit on opposite sides of the Earth at an altitude of about 600 kilometers. Each GCAM satellite features a dome-shaped array of 25 gamma ray detectors and 8 charged particle detectors. They'll search for cosmic events happening in the energy range 6 kilo electron volts to 5 mega electron volts. With a couple of minutes of detection, GCAM will send out alerts to telescopes around the world for follow-up observations. See Lynn's on the call. For those of us that heard Lynn's talk about the solar cycle, I rather like this image that I found on the net. For a quarter of a century, the ESA NASA Solar and Heliospheric Observatory, or SOHO, has been essential in helping scientists understand the heart of our solar system, the sun. The SOHO mission launched 25 years ago this week, and to celebrate, ESA compiled a wonderful mosaic of images. This shows the 11-year solar cycle as described by Lynn rather nicely. SOHO was launched on December the 2nd, 1995, and was only designed to last for 2 years. But the spacecraft showed itself to be a workhorse, and the mission was so successful that ESA and NASA decided to prolong its life several times, granting several mission extensions. Some of the highlights of Soho's revelations have been the first images ever of a star's convection zone and the structure of sunspots below the surface, the most detailed and precise measurements of the temperature structure, the inner rotation, and gas flows in the solar interior, discovering new dynamic solar phenomena such as coronal waves and solar tornadoes. It's revolutionized our ability to forecast space weather by giving up to 3 days' notice of Earth-directed disturbances and playing a lead role in the early warning system for space weather. It also monitors the impact of solar variability on Earth's climate. A new image from the world's largest solar observatory shows a spectacular high-resolution view of a gigantic sunspot. This sunspot measures about 16,000 kilometers across, large enough that the Earth could fit inside. The image was taken by the new Daniel K. Inouye Solar Telescope located in Hawaii. Scientists say that the new observatory, with its large 4-meter primary mirror, will enable a new area of solar science and provide a leap forward in understanding the sun and its impacts on our planet. And for those of you who've got a few bob saved up from not going on holiday this year, how about something extravagant for 2021? Virgin Galactic is set to carry out a milestone test flight of its rocket-powered tourist plane this Saturday. This will be the first crewed flight of its reusable Unity vehicle to take off from the purpose-built commercial spaceport in New Mexico in the USA. Sir Richard Branson's company will begin space tourism flights in 2021. Already, more than 600 paying customers, including Justin Bieber and Leonardo DiCaprio, are booked to take a ride in the plane. As far as I can make out, the tickets are $250,000 each, so I think I'm going to give this one a miss. The Stingray Nebula is the youngest known planetary nebula. For half a century, astronomers have witnessed its formation, and now they've noticed something strange. It's fading away. This is very, very dramatic and very, very weird, said Martin Garano, one of the co-authors of a new study on the Stingray Nebula. What we're witnessing is a nebula's evolution in real time. In a span of years, we see variations in the nebula. We haven't seen that before with the clarity we can get with this view. Between 1996 and 2016, successive Hubble images of the Stingray Nebula revealed that it's getting weaker, dimmer, and less prominent. It's the shadow of its former self, as you can see, and getting weaker by the day. As an example, the brightness due to the presence of ionized oxygen has dropped by an unprecedented factor of about 1,000 in the 20 years between the observations. Thanks to the guys at University Today for sending out their newsletter that gives me most of the up-to-date information we can use for space news each week. And that's it for tonight. So back to Alice Amanda.
Right, thanks very much for that, Roy. That was interesting. Aye.
Yeah, very good.
Aye. I mean, I think I'll be giving the space flight a miss and all, $250,000, even if it isn't dollars. No, I think we'll just bypass that.
I reckon.
I don't fancy having that much fuel propelling me up. But I mean, one mishap and we could be gone.
Indeed.
Any passing of wind or anything, and the next thing.
Passing of wind was a strange comment, but no.
Well, you know what I mean? If you're sitting there and next thing, wow, you know, who knows? But anyway, it was very interesting. It was interesting to see the Stingray Nebula and how that's decreased in brightness as well.
Yeah, it's cool.
Mm-hmm.
Yeah, so I don't know. Wonder what's causing that. Is it just its age?
I think it's just dissipating. That's all they are.
Aye. Right. Right. Right, now on to our main speaker. Dr. Luke Daly is a lecturer in planetary geoscience in the School of Geographical and Earth Sciences. He studies space rocks to understand where Earth got its water from. He is a participating scientist on the Japanese Space Agency's Hayabusa 2 mission to return samples from the asteroid Ryugu and co-leads the operation of the UK Fireball network to find meteorites in the UK and try to find out where they come from. So let's give Luke our usual warm Kaz welcome. Right, and can everybody mute themselves?
And shall I share my screen?
It does that. I think it
That's it.
Watch the screen. I can do it.
Just move everyone's faces out of the.
Screen
Can everyone
changes.
see that screen?
That's it. It's there, Luke. Thanks.
Beautiful. Awesome. No, yeah, thanks so much for having me. It's a real pleasure to be speaking to you today. Thanks for the invitation. Yeah, so my name's Luke Daly. I'm a lecturer at the University of Glasgow. And so this talk is sort of introducing you to sort of key question we have in planetary science, believe it or not, which is where do meteorites come from? And meteorites just being space rocks, and how we can use ground-based camera observatories to try and find them on the ground in the UK. So that's going to be what this talk is about. So what are meteorites to start with? For those of you who are not planetary scientists and haven't come across what a meteorite is before, they're essentially just rocks from space. They are split into three main types. There are stony meteorites, which, as the name suggests, are made out of stones. There are stony iron meteorites, which are made out of stones and iron. And there are iron meteorites, which are made out of iron metal. And we study these in planetary science to try and understand how our solar system came to be and how you build planets. So, for example, the iron meteorites are super useful rocks and samples to get because they represent the core of a busted up planet. So when a planetary object gets big enough that it melts, the iron, nickel, metal sink down to the center of the body to form a core structure. Then you have a mantle and a crust. Our planet has this composite, this kind of structure. Iron meteorites represent that core material. And so they're really important for us to study because that gives us an understanding about how planets form in the first place. But they're really important for understanding our own planet because we can't get a bit of our core. It's really dark and hot and squishy down where our core is. And so we just can't drill down deep enough to get samples from it. So fortunately, some poor planetesimal early in our solar system's history got busted up for our science, and we now fragments of it rain down onto Earth, and we can sample them and go look at them to find out what our own core is made of, which is really cool. The stony iron meteorites, for a long time, we used to think they came from this core mantle boundary between the sort of like these layers in the sort of differentiated planet structure. However, some recent work by my friend Claire Nichols down at the University of Oxford now has shown that they actually probably came from or preserve evidence of some of the most climactic events in our solar system. And that's when two planet-sized objects collide with each other and merge. So these, what are known as palisite meteorites, are these beautiful meshworks of stone intermingled with iron, nickel, metal, and basically are evidence from when the core of one planet merged with the mantle of another planet early in our solar system's history, which is really cool. And then the sort of final group, the stony meteorites, is where I spend most of my time researching. They're the ones closest to my heart. They're split into two. There's the achondrites, and they come from the crust of planets. And so we have achondrite meteorites from bodies like Mars, from the moon, from an asteroid called Vesta. And we can study them to understand volcanic processes, and so what volcanic systems are like on other planetary bodies in our solar system that we have meteorites from, which is really nice. And then the other type is called the chondrites, which chondrite just means it has chondrules in it, which are these tiny spherical igneous melt droplets, and the solar system's first lavas. And the chondrite meteorites are possibly my favorite because they are the oldest rock you'll ever hold in your hand. All the minerals, all the grains inside them formed within the first few million years of our solar system's history. So these grains, these rocks are witness to the formation of our solar system right when the sun first started to shine. And so we can explore these things to figure out how our solar system came to be in the time before there were planets. I'd like to also quickly, before I get into the guts of the talk, get some definitions out of the way, because one of the key questions I always get is, what's the difference between a meteorite, a meteor, and a meteoroid, which is kind of the three ways we describe these kind of objects. And just to kind of clear the air, a meteoroid is just a space rock that's still in space. So it's still floating around outside of the Earth in the void somewhere. A meteor is simply just a light in the sky. It's got nothing to do with the rock itself. It's the light you see as that rock passes through Earth's atmosphere, and the friction forces cause it to the outer surface to heat up to sort of a plasma, and that generates a lot of light, and that's what we see as a meteor. Otherwise known as a shooting star, or if it's really long, we call it a fireball. If part of that space rock is lucky enough to hit the ground and hit the deck, then it becomes a meteorite. And this kind of confuses me in many ways, because there is literally no difference between a meteorite on the ground and the meteoroid in space. It's the same rock, it just magically changes its classification to a meteorite. And I always kind of wondered, you know, what would happen if you caught it and then dropped it? When does it become a meteorite from a meteoroid? Something that amuses me. But anyway, as I was kind of getting at, what we're really interested in planetary science is getting at the question of, how did our solar system form? How do we build a solar system? How did we go from this big ball of gas and dust called a giant molecular cloud, collapse that down under its own gravity till the center of it has the pressures and temperatures required to kickstart nuclear fusion to generate a star? How does that gas evolve into a disk-like structure called a protoplanetary disk around that young sun, the swirling disk of gas and dust? How does that gas and dust interact with each other, come together to form bigger and bigger objects, to asteroids, to planetesimals, to eventually a fully fledged planetary system like ours, with the third rock from the sun that has life on it that's arguably intelligent? So these are kind of like the big picture questions we're trying to get at. And there are a number of ways we can try and sort of attempt to answer these questions with some of the nice observations we can make. The first thing we can do is, if you're from an astronomical perspective, go look at some large telescopes like the ALMA Space Telescope. And this image here is a beautiful image of a protoplanetary disk captured by the ALMA telescope of a star with its protoplanetary disk around it forming right now in our galaxy. And this really changed the game of what we thought these disks looked like. We used to think they were these single homogeneous masses. And the kind of key thing you can see from here is you have this beautiful structure. So you have these ring-like systems. And this seems to now be pretty common in new formed planetary systems that we're seeing through the ALMA telescope, which is amazing. And that would segregate, the effect that would have, which would segregate your protoplanetary disk into distinct regions that are isolated from each other. And potentially that would allow you to get different meteorite types and different planet types in each of those rings, which is really cool. However, we can also look out sort of more locally to see what our solar system looks like now. So this is a sort of amalgamation of the observations of near-Earth asteroids in our local neighborhood. And you can, all these dots that are orbiting around our sort of like local area get more and more and more the more and more we look, and we're tracking nearly like 90% of everything above the size of a house in our local neighborhood. And so it's getting quite busy and quite hairy. There are thousands and thousands of objects in our local neighborhood. Luckily, none of them are coming anywhere near us in the next 100,000 years, so that's kind of fine. We're happy with that. But this obviously looks very different to that nice ordered structure I just showed you with the ALMA telescope. And one of the questions has been, well, how did that come to be? How did we go from this ordered ring-like structure to having an asteroid belt? And that's where a theory called the Grand Tack hypothesis comes in, which is essentially just throwing Jupiter at the problem. And this was actually invoked to explain why Mars is really small, believe it or not. So Mars formed further out than the Earth, and it would have had a lot more of that protoplanetary disk material to form from. And all our models should predict that there should be two Earth-like objects, or a super Earth even, where Mars is. But Mars is substantially smaller than the Earth right now. And the kind of question was like, what happened? And this Grand Tack hypothesis suggests that Jupiter formed early and then migrated inwards and nicked all Mars's stuff. And then before it went all the way into the inner solar system to form a hot Jupiter, Saturn formed, migrated in with it, and then dragged it back out in a resonance kind of effect, back out to its current position, sort of leaving Mars with a little bit of stuff to form from. And so that's why we have Mars being quite small. And that seems like a really big sort of way to solve such a relatively small problem, is throw a gas giant planet at it. But this also explains potentially why we have the asteroid belt we have today, which is a jumble of lots of different asteroid types. So what would have happened is all the asteroids in the inner solar system that were forming as Jupiter migrates inwards would have been scattered out into the outer solar system. And then as Jupiter migrates back out to its current position, all the outer solar system objects would have been thrown inwards, turning the inner solar system into a kind of horrible pinball system for a while, but eventually settling everything in the asteroid belt in this kind of jumble. And that's where we are kind of now. We have our sort of asteroid classification, where we look at the light reflected off these asteroids and we can classify them in different types. And you can see there's none of the structure that would be suggestive of that nice ring system we see in other protoplanetary disks. But then we also have meteorites on Earth. And the meteorite, don't worry about these figures, they're kind of both. This is the meteorite classification system. And as you can see, it's an alphabet soup of hell, where we've kind of split all these space rocks into lots of different clans, groups, based on their chemistry, based on their isotopes. But what we really want to do is be able to link meteorites on Earth with asteroids in space to try and tie those two together and start interpreting the events that sort of this chain of events that resulted in the formation of our solar system and the planetary system we observe today. And that's where kind of space missions come in. Hayabusa was a Japanese space agency mission to the asteroid Itokawa that landed on that asteroid and brought us back literally about 300 grains. I was lucky enough to get 3 of them to analyze, which was really exciting. We found some really awesome stuff with that I'll go into a bit later. There was also NASA's Stardust mission, which went through the tail of a comet. So we now have bits of comet back on Earth. And there are 2 missions that are ongoing right now. One is NASA's OSIRIS-REx mission, which landed on the asteroid Bennu. And then there is the JAXA, or Japanese Space Agency mission Hayabusa 2, which has sampled the asteroid Ryugu. So the sort of space agencies are really interested in going to sample these extra solar system, these solar system objects to figure out what they're made of and try and link them to stuff we have on Earth. And of course, no list like this would be complete without the Apollo missions, and mentioning that sort of the thing that started it all really in terms of sample collection from the extraterrestrial environment, bringing back kilos and kilos of lunar material that really sort of changed our understanding of how the Earth-Moon system formed, which was amazing. Now, I mentioned these missions that are ongoing right now. Just the other week or month, I believe, the OSIRIS-REx mission landed on its asteroid. This is that video there, and took a sample in its touch and go maneuver. It actually did way better than it was expected. It couldn't actually close the sample canister because they'd caught so much material. So that's amazing. And that's now on its way home and will be back with us in 2023. And then as exciting, if not more so, the Hayabusa 2 mission, this was a year or so ago, did its own touch and go maneuver on the asteroid Ryugu, going down, shooting a tantalum bullet at that surface, kicking up a load of dust. Some of that dust has gone up the sample canister. And then just a week or so ago, this image was taken as that sample canister comes blazing through the Australian skies and landed in Woomera in South Australia, and is now back safely in the Japanese Space Agency complex in Sagimihara. And they just today, I literally got sent this message, an email just this afternoon. They had opened the canister and they can see all this very fine sand-sized particles, which is material they've sampled from that asteroid. And I'm really lucky and really excited to be part of the fine-grained sample analysis team. And I'm going to be getting 3 whole particles from this. And if anyone's listening, I want this one, and this one, and this one. I don't know why, but they just look cool. So what these allow us to do is make that direct link between asteroids and meteorites on the ground. So the Itokawa mission was spectacular in its success and allowed us for the first time to go, S-type asteroids like this Itokawa object are the source for L chondrite meteorites. So the ordinary L chondrite meteorites we have on Earth probably come from S-type asteroids like Itokawa. And that's really powerful and allows us to do some really cool things in terms of interpreting our solar system. However, these missions are quite expensive. The Hayabusa mission, for anyone's up on their Premier League football trivia, costs one Neymar Jr. Or about £200 million. So these are not cheap missions to go out and sample asteroids. And fortunately, space comes to us for free all the time in these beautiful events called fireballs that sort of evidence of space rocks flying through our atmosphere. I'll let that image go again because it's just really spectacular. And if we're lucky, occasionally some of these events, some of that meteoroid survives that fiery transition and lands on the ground as a meteorite that we can then go and recover. And we've got really good at this. So one way we do this is taking advantage of the properties of meteorites. As they've come through the atmosphere, the outer surfaces become like molten, and they generate this very black crust, which we call a fusion crust. And so we can go to areas where the surface is stable for a long period of time, and you have really nice contrast, like Antarctica, to go hunt for them. So the ANSMET mission, or the Antarctic Search for Meteorites expedition, goes out every year alongside a Japanese mission, a Belgian mission, and for the first time a year or so ago, the UK led its first meteorite recovery expedition to Antarctica, essentially going to these ice fields where little black rocks on the surface of that ice field stick out like a sore thumb, and most of them are meteorites. And it takes advantage of this really interesting sort of property of, as the ice of the glaciers comes up against the mountain ranges, the wind flow over that surface ablates away that ice, sort of turns it into a vapor immediately, and acts basically as a vacuum cleaner, sucking these meteorites that have landed elsewhere on the glacier up and concentrating them all in one place. And then it kind of just becomes too easy in many ways, apart from, being in Antarctica where it's freezing cold and there's blizzards all the time. Literally, when you have nice clear skies, you can just walk across and every black rock you see is a space rock. So there's over 60,000 meteorites now in worldwide collections because of expeditions like this to Antarctica and other areas like hot deserts where meteorites are concentrated and preserved, and we can recover them. However, there's a key issue with all this. We're lacking their context geologically. We've just got 60,000 random space rocks, and we've got no idea where in the solar system they come from. That's kind of like, if you're sort of from a geological perspective, if you've got 60,000 random rocks from Scotland dumped in your back garden with no context, and then someone asked you, okay, figure out how Scotland came into being, what's its geological history? It's a very challenging task. You can get part of the way, but you really would like to know where these rocks all come from. And so we're missing that key piece of information, and that piece of information is their orbit. So that orbital information of, if you can see that fireball as it comes through the atmosphere, you can figure out where it lands and also figure out where it came from in space and tie it back to an asteroid or asteroid family. And then you can start doing some serious geology and reconstructing our solar system's history. And that's where camera networks come in. I'm going to talk about the Desert Fireball Network, but of course there are other camera networks all around the world doing a very similar thing. And the idea essentially is to put cameras out in remote locations to image the night sky all the time at night, to image these fireballs as they come through from multiple positions, to then triangulate the space rock down to the ground and go recover it, and also be able to figure out where it came from. So I was lucky enough to be part of this Desert Fireball Network in Australia for my PhD, who the PI was a Professor Phil Bland. And we set up these autonomous camera stations, sort of like this nice solar panel camera system on top of a platform, wires to protect it from the local wildlife like cows and kangaroos and camels, believe it or not. And essentially set up a number of these systems that could sit there clicking away all night, every night for years. So this is another one of those camera stations. These can act autonomously for over a year. Australia is a fantastic place to image the night sky, particularly in the outback. There is zero light pollution, and the sky is just full of mesmerizing stars. The Milky Way is visible almost every night, as are the Magellanic Clouds. And so, yeah, it's almost like the perfect place to go install a camera network to try and image fireballs. We installed 52 cameras in the sort of stage one of the project. So that ended up covering about 1 million square kilometers of sky, which is about a third of the continent. And so we were able to sort of image quite a large area. And from that, we were able to get quite a lot of fireballs. This is an example of the data we got from one of our digital cameras. One of my colleagues, Dr. Robert Howie, was added in a very clever system to figure out when the fireball came into our image. So our images are around 30 seconds long. And of course, that's quite precise, but you want to know much more detail about when precisely that fireball came in that 30 seconds. And so he invented this thing called a De Bruijn sequence and embedded that code into the image itself. It's essentially the shortest non-repeating sequence you can fit in a given time frame. And what it does is it splits the image into these long and short dashes. So as a very fast moving object comes through our field of view, it is split up into these long and short dashes, and you can measure the distance and the gap between them to figure out to sub-millisecond precision when that fireball turned on, when it hit the top of the atmosphere and started burning up, and when that light went out. Some of our cameras have been spectacularly successful at this. This one from Haydn has seen several hundred fireballs. It's basically worked completely fine for years now, which is amazing. Obviously, we're taking pictures and we don't get to choose what we see half the time. So they're also quite nice roosting positions for birds. So sometimes your whole night is this, but thankfully that's not all the time. And at the very start, we kind of realized that we were generating a substantial amount of data. 52 cameras taking a picture every 30 seconds is almost 1,000 images per camera per night. And you do not want to be the grad student, which was me at the time, going through those 1,000 images per night trying to find fireballs. And so we developed, or the group developed, this kind of automated pipeline where the camera would be able to calibrate itself, detect the fireball events, be able to distinguish them from like planes, satellites, that kind of thing, process that image, talk to all its neighbors, figure out if they saw the same event they did, as well as do a rough and ready triangulation, mass calculation, full position and orbit. So basically all the work is done by the time the camera has figured out it's seen a fireball event that dropped a meteorite, and then it pings us. This is what we then get. These are sort of like these cameras nodes we have around Australia. And this is a fireball event that was seen by multiple stations. And then it's basically a game of doing trigonometry in 3D. All those planes intersect and form that line where they've seen the same fireball. And you can then triangulate that down to the ground, model it through its dark flight, but also then triangulate it back out into space to figure out its orbit. Then my colleague Ellie Sansom has done some amazing work sort of modeling, sort of predicting the mass and the shape of these objects as they come through the atmosphere from the data we collect. And from that, we're able to predict what's known as a strewn field. So basically a range of area on the ground where we think meteorites of different masses and different shapes will have landed. And then we can get in our trucks, drive out into the middle of the Australian outback and go searching. And the scenery is spectacular. The searching terrain is amazing. I mentioned Antarctica is really good because it's white ice. Australia is barren, lifeless red dirt, and black rocks like meteorites stick out like a sore thumb. It's also covered with salt lakes. Again, these are perfect searching terrain. And this is an expedition I was on to try and find one particular meteorite, and we were really hopeful, seeing this terrain, that we might be successful in recovering it. The terrain, like I said, was really good. And the way you search for a meteorite is kind of like body searching. You all line up in a line of sort of a few meters apart. Each person at the end has a GPS to keep track of where you are. And you just walk across the Australian outback for kilometers and kilometers, trying to find a little black space rock. About day 2 of this trip, we were about sort of 2 hours or so from camp, and we see these kind of like rain clouds gathering on the horizon. And we kind of look at each other and go, okay, it's about 45 degrees. We've done a good job today. Let's go home before this hits. About an hour away from camp, we look back again, and it's turned into quite a substantial thunderhead. And so we start sort of like quickening our pace to get back. Then this sort of like dream theater style concert sort of erupts behind us when we're about 10 meters away from camp, 10 minutes away from camp. And then we just literally get back to camp, dive in our beautiful Faraday cages, which are our cars, before this happens all around us. The heavens literally open and turns our camp into a lake very briefly. This happened for the next 5 nights, and we were kind of concerned we wouldn't get out of this area. So we kind of called off the search and sort of evacuated this area. And then I got banned from field trips because this has happened every time I've been to the outback of Australia, which, considering it's a desert, you shouldn't get rain all that often. And it literally happened every time. So they kind of Jonah and the whaled me, and I got put on the naughty step. But then we got a bit luckier. We saw this fireball initially from 4 cameras, but it turns out other cameras had seen this as well. This was really brilliant, bright green fireball in sort of towards the end of the year. And what was really nice about it, has a really steep trajectory. So it came in at a really steep angle. So our strewn field was then going to be really small. And we're pretty sure this dropped a rock. It also, I'm not sure if you can see from this Google Maps image, landed directly into the middle of the largest salt lake in Australia, Katitanda Lake Air. So again, white salt. This is going to be a really good place to try and find a meteorite. So the crew went out without me, obviously. I was still banned. And what was really nice about this is because Katitanda is a sort of a special sacred site for the local Aboriginal communities, we were able to sort of talk with their elders, and sort of they permitted us to go onto their land and even helped us find the right routes onto the salt lake that would avoid us getting bogged down and sort of having to call off the search, which was just amazing to sort of be able to work with these people. We also got the local Air Force involved to help us out with the search. The sort of like local light aircraft took some of our researchers up to see if we could see the meteorite from the air. And this was the search zone we were kind of looking at. And again, like really nice contrast. The black rock should stick out like a sore thumb. Although I'll note it's not just me that causes problems. You note on the horizon, there's again storm clouds gathering. There was quite a substantial storm inbound when they got onto the Salt Lake finally, and they probably only had about 2 hours of searching. You can see the sort of clouds are coming in. The airplane was flying overhead. The ground team was searching across the Salt Lake on quad bikes. The plane saw this, that's it, right? That's where the splash zone is. That's a meteorite coming in and landing on a salt lake. But because it was seen by the aircraft, that plane, then we didn't get a good GPS log. And so we lost it again. And this is the GPS trail of us frantically trying to find this area. And then just as we were kind of about to give up and get off the Salt Lake before the storm hit, Phil saw it, my boss. It's actually in this image, believe it or not, this thing here. Anyway, he legs it over and starts digging with his bare hands into the mud, this like thick, congealed, sticky salt lake, down about 1/2 meter, and eventually, sort of with this like sucking sound, pulls out a little space rock, which is it's not an iron meteorite, it's a H5 ordinary chondrite. Phil was just so exhausted from digging down a meter that it felt super heavy in his hand. But yeah, so this was really great. We recovered this meteorite in Katitanda Lake Air. The elders of the local Aboriginal community were kind enough to name it for us after a local area that this meteorite was found in. It was recovered on New Year's Eve, believe it or not. Which was amazing. It had penetrated about 1/2 meter into the ground. It was about 1.5 kilos, so a substantial chunk of space rock. And then the team hightailed it out of there because then the storm broke and Katitanda Lake Air filled up for the first time in 100 years. So we were really lucky to get this rock. It was a really kind of fortuitous, serendipitous find. Obviously, my boss at the time was super happy, and my colleagues. And because this basically shows that our hard work over the last 5 years of developing the pipeline, installing the cameras, developing all these algorithms works, and we can get space rocks on the ground from these camera observations and figure out their orbit. So we have the orbit of this Merilli meteorite, and we're able to link it to sort of like, well, in the future, we'll be able to link it to asteroid families in between Mars and Jupiter, which is really cool. We also recovered one which fell on Halloween. I'm not really sure what it is about pagan holidays and meteorite finds in the UK, in Australia, but here we are. So this fireball event was seen. We were able to get a really nice orbit from it. However, the problem was we only saw it from the south, in and around Perth in West Australia. And so our initial stream field wasn't very well constrained. It had some quite large errors with it until a citizen scientist sort of phoned in and reported their observation using our Fireballs in the Sky app, which saw it from the other side. So we were able to kind of constrain the trajectory a lot better and figure out where it landed. My colleague Ellie Sansom sort of applied some of her models to this, and you can kind of see how good her models are, that they were able to find the meteorite within about 200 meters of where it was supposed to be based on her models, which was fantastic. And the speed of the network, because it was automated, we were able to get out there and recover it within about 48 hours. So this meteorite, when we cut it open, is possibly the most pristine meteorite we've ever had, because it was recovered so quickly. No rain had fallen on this rock. So it's been completely unaffected by any Earth processes and is now in sort of like quite sophisticated curatorial facility, so it doesn't get altered by being in contact with the terrestrial atmosphere or Earth's atmosphere. And so there are going to be some very delicate minerals that we normally don't see in this rock, and I'm really kind of excited to kind of see what we find in here. So that's the state of play with the Desert Fireball Network. As well as those finds, we've also imaged thousands of fireballs, and we were able to map out where they are and start understanding where these things are coming from in our solar system. So the orange lines here are the orbits of fireballs, and the teal dots are the meteoroids themselves coming to hit that third rock from the sun and then being imaged by the Desert Fireball Network. And what's really cool about this is there's over 1,000 fireballs in this image. We can start seeing where stuff is coming from in our solar system. Like this is the Geminid meteor shower just coming in here, just about to completely nail us like now. And so this data is becoming really important to understand where material is being delivered to the Earth from in our solar system right now. Off the back of this success, the project's gone global, and we're now taking this concept around the world to set up what's called a global fireball observatory. So that'll be the Desert Fireball Network in Australia, as well as some nuclear networks in other sort of locations. So we have networks cropping up in the US, Canada, Saudi Arabia, and Morocco. And because I'm no longer at Curtin, I'm now working at Glasgow, I'm helping with colleagues at Imperial College London to set up the UK Fireball Network, which is the UK arm of this. And the aim of this project is to essentially be able to image the night sky in both hemispheres 24 hours a day. So we're seeing everything that's flying in Earth's atmosphere the whole time, primarily to find meteorites. We should cover about 2% of the Earth's land surface or sky by this project, which will result in about 5 meteorite falls a month, which is a lot. And over the 5-year lifetime, that will translate to about 300 meteorite falls. And so statistically, we should get at least 1 meteorite from every single class of meteorites. So even rare stuff like Martian meteorites, lunar meteorites, potentially even a comet will get in the next 5 years, or at least see it fall, if not recover it. And in each case, we'll be able to get the orbit. And so what we're essentially doing is a sample return mission where the samples come to us and we then figure out where it goes, rather than sending a probe to the asteroid to figure out what meteorite it's come from. So it's kind of doing it in reverse, taking advantage of the sort of solar system dynamics to bring us samples. So the UK Fireball Network is what I'm setting up and or have set up with colleagues at Imperial College London in the UK. We have a few challenges that Australia didn't have. They have the really nice searching terrain of barren red dirt. Our searching terrain is substantially harder with sort of deciduous forests, or if you're up in Scotland, these sort of like boggy peatlands that are sort of very sort of like dark greens, dark browns, have very low contrast compared to the black fusion crusts of meteorite. So searching is a lot more challenging. Also, the weather's against us. You get a lot more overcast days in the UK, as I'm sure you're all aware, rather than the sort of like gorgeous sun you get in Australia. But despite this, it's still possible to recover meteorite falls. And the reason I know this is we have precedent here. The last one in Scotland was over 100 years ago, which was the Strathmore meteorite, where people saw this bright fireball on the 3rd of December 1917. It was a airburst meteorite, so it burst in the upper atmosphere, split into 4 chunks, one of which absolutely nailed this woman's house. However, not everything is not quite as it seems in this GIF image. The Strathmore meteorite did indeed cause substantial damage to this poor lady's house. However, by the time the media had got there, it was a few days later to take this image. And of course, you don't want a big hole in your house in Scotland because it rains all the time. And so they'd already fixed it. Kind of not to be dissuaded, the journalist kind of took some initiative and inked in the hole artificially with a pen. And so this is possibly one of the first examples of fake news in the modern media, which I kind of like. It was kind of fun. Also, like looking into sort of researching this, some of the news clippings that come back, realizing clickbait is not a new phenomenon. It's been around since the 1917s, with things like bombshells from space, a scintillating incandescent mass, and heard it fizzing, which sort of gives you a really fun window into the early 90s Scotland. And then the last one in the UK as a whole was the Glatton meteorite, which fell on the 5th of May 1991, so 29 years ago. And that was also an ordinary chondrite type L6, and it landed in near Glatton in a chap called Arthur Pettifor's back garden. And again, his kind of account of the matter was kind of hilarious, saying he heard a whistling noise and then a disturbance in his conifer hedge, and felt lucky not to have been hit by it, but was more alarmed that it narrowly missed his greenhouse, which kind of gives me a fun indication of the sort of priorities of this person. Who has a space rock land in his back garden and cares more that his greenhouse is still intact, which is fun. However, we should in the UK get one meteorite of a searchable size per year. And what I mean by that is something about the size of your fist or about the size of your thumb. We can go search for and recover something that size. However, we haven't recovered one or seen one and then recovered it for nearly 30 years now. So we're batting way below our average. And that's where the UK Fireball Network comes in to try and rectify this. This is a light pollution map of the UK. And what we want to do is steer away from these horrible red, white areas of high light pollution like London, Manchester, and Glasgow, and kind of stick around these dark sky parks, these clearer light blue areas. We have another advantage from the camera network in Australia because we're not as big as Australia. So while they took 52 cameras to cover 1 million square kilometers and only a third of the continent, we only need 12 to cover the whole of the United Kingdom. And also, despite the fact that we have quite a lot of overcast days, when it does clear, as I'm sure you're all aware, you get some absolutely stunning skies above the UK. So here's an example of a fireball in the sort of northern reaches of Scotland. And so we're quite confident that we're going to be able to see fireballs on a regular basis and recover meteorites should they fall. So we've installed 6 cameras as of today, one in Galloway in Scotland, 4 across the spine of the UK and 1 in Wales. We have plans to sort of fill in the rest of Scotland as well as Northern Ireland and Cornwall once the kind of COVID crisis is over and Australia opens its borders and allows the cameras out to be delivered from the Australian Desert Fireball Network to us over here. And these are kind of what our setups look like. So we have basically these tripod systems or attached to roofs with our nice digital cameras, both video and stills. The inside, the guts of our cameras looks a bit like this. So you have your literally off-the-shelf Nikon DSLR with a Samyang fisheye lens, the sort of computing hardware that does all our event detection, and then kind of 3 8-terabyte hard drives, or literally as big as we can put in to store the data. And so this system can act on its own for the next 18 months without us having to look at it, which is really cool. So this is one of the first systems we installed, which is on my colleague Martin Settle's house in the south of England, which is a really nice system. It's been working really well for us. And this is kind of a day in the night of what that camera sees. So you can see planes going overhead. But I guess the kind of key thing to notice here is we have that cloud cover issue that I mentioned. But however, sort of eventually, when this clears, hang on one second, any time now. When it clears, you do start seeing stars. You do start seeing sort of really nice sort of stellar phenomena, satellites, planes. And if a fireball came through right now, we would see it and pick it up really nicely. And that's basically exactly what we've been doing recently. We had a really nice fireball straight out the gate on the 3rd of November with this event. And this one on the 12th of November, this was back in 2018. And so even though we weren't able, this was only from a few cameras, so we didn't get to do a decent triangulation or figure out if it dropped anything, we started getting data. And at this time, we were also starting to sort of talk to the rest of the community in the UK, and we realized we weren't the only game in town trying to do this. There were a lot of really awesome, both amateur and professional networks already established in the UK, imaging the night skies to look for meteors and fireballs. One of which was SCAMP, or the System for Capture of Asteroid and Meteorite Paths, which is an extension of the French fireball network, FRIPON, they use a different system to us. They use video cameras with an all-sky lens rather than still digital camera images, but still sort of do the same thing we do in a very slightly different way. And they're led by Jim Rowe. I really like SCAMP in many ways, particularly it's a masterclass in acronyming. So the FRIPON network, if anyone's up on their French, FRIPON is French for mischievous small child. And SCAMP in English is the same meaning. So whoever came up with that was a genius, and I applaud them and tip my hat to them. There is also the UK Meteor Observation Network, or UKMON, who use CCTV cameras. So these are sort of more narrow angle video cameras, primarily designed to image meteors, but they do capture fireballs as well. As well as there's also the Nematode Network and the Global Meteor Network, and then just a plethora of awesome sort of amateur astronomers with all-sky observatories in their back garden that are imaging the night sky. So we realized there's this huge community and huge infrastructure already in place, all trying to do the same thing, and that's image meteors, image fireballs, and recover meteorites with orbits. And hopefully you're thinking what we were thinking at the time, is like, hey, why don't you all work together? And that's exactly what we did. And we sort of initiated a thing called the UK Fireball Alliance, or UK Fall, which brings together the professional networks, the amateur networks, as well as interested academic institutions, as well as curatorial facilities like the Naturalist Museum in London, the Hunterian Museum in Scotland, and the Cardiff Museum. So a bunch of people who are interested in finding that first meteorite in the UK for 30 years. And so what this allows us to do is share data, share models, and to be able to rapidly respond to a fireball event should a fireball drop a meteorite on UK soil. The first kind of joint observation was around 15th of Feb 2019, which was a fireball event over Belgium. And I saw that on the news and kind of didn't think anything about it because I was like, Belgium's a bit far away. But then UKMON and FRIPON said, we saw it, check your cameras too. And then we looked in and we're like, oh, we got it as well. And now if you're wondering, I did this as well. This is the moon. And I was initially like, wow, that fireball's huge. No, it's this little thing over here going behind this tree off over the channel into Belgium. But so what was really nice about this is we realized we were seeing much further than our field of view, well, at least what we thought our field of view was. And then another example happened this year, just before everything went to hell. On the 16th of February 2020, UKMON saw this fireball. We saw it really nicely. And then FRIPON saw it twice, or SCAMP saw it twice, sorry. And then we were able to sort of share data, bring it around the whole group, put it through all our different models, and we got a really nice orbit from it. And it looked like around 10 grams of material actually survived from the fireball and would have produced a meteorite. And so we were like, okay, great, this is awesome. 10 grams, we can go find that. Where did it land? And then we realized there was a small problem because this landed directly into the North Sea. So unfortunately, no meteorite recovery expedition for this one. Yeah, even scuba gear is not going to cut it, I'm afraid. But what was nice about this demo and seeing this event showed that the UK Fall initiative works. We can share data rapidly with all these different networks, translate them into a different format that is readable by all the different networks, put them through our models and figure out where we've got a meteorite really quickly. And so that's really good looking at the future. I'd like to quickly go through some other interesting stuff that I think you might be interested in, because one of the kind of fallouts of having a global observatory of cameras that are constantly clicking away and seeing the night sky is we don't just see meteors, we see everything that's flying around up there, and including satellites. And we kind of realized that we were seeing satellites and multiple cameras were seeing the same satellite, and we were able to triangulate them. And this gets us into some really interesting sort of planetary protection, space situational awareness problems. If you've seen the film Gravity, you know what I mean. But there was also sort of been some very near misses as the space environment, the near Earth environment gets busier and busier. with different satellites. And it's only going to get worse with these super constellations. So, for example, there was a near miss where the Cosmos Russian satellite was on a collision course with the Fermi satellite. And NASA was talked to the Russians and say, hey, we're on a collision course. Can you move out the way? And the Russians were like, no, we don't have control of that satellite anymore. You need to move. And so Fermi had to take evasive action and move to a different orbit to get out of the way of this Cosmos satellite that was out of control, which substantially reduced the lifetime of that mission or its capability. It had to burn a lot of fuel. And so this is kind of a really important thing to be getting into. And we developed a new system of cameras, and you can kind of see satellites going across here than ever. You can even see these little dots. That's not a bit of dust on your computer. That's a geostationary satellite, which is really nice. And there's a fireball about to go through here in a second. If you saw it just go past, I'll just take it back and let it play again. We'll go back a bit further. If you look at this area here, a fireball comes through this image, and it has a little sort of like cloud trail just there, which is really nice. And my friend Trent Jansen-Sturgeon did an amazing job of essentially generating a real-time database that refreshes every 6 seconds of all the stuff this camera system was seeing. And so we're able to see everything that's flying around up there above where we have cameras. So including the geostationaries, including the sort of low Earth orbit satellites, which is really nice. We also see some weird events, and this is an event that we saw, and I'd like to kind of focus your attention on this bright light up here, which we didn't know what to make of for a while and concerned us. So this was a bright event that instead of going down was going up, and then it changed direction. And there are suddenly very few things that can be, certainly nothing natural. And my colleague Hadrian had the bright idea to triangulate it back down to the ground to see where on Earth it came from, literally. And fortunately, it sort of tied back perfectly to the Chinese launch facility and was a sort of scheduled launch of one of their satellites. And so we, again, kind of realized with seeing the night sky all the time, we'll see people launch rockets into space by using these very simple off-the-shelf digital cameras, which is really nice. We're also able to help participate in the sample return missions to asteroids themselves. So the team was involved imaging the OSIRIS-REx flyby when it did its gravity assist of the Earth on its way to the asteroid Bennu. They also helped with the imaging the sample return of Ryugu 2, of Hayabusa 2 from Ryugu. I am told in good faith by people I trust that OSIRIS-REx is in this lower image. I am yet to find it, but they tell me it's there, and they were able to figure out its trajectory, that it showed it was safely on its way to Bennu. And then finally, one of the more strange things we were able to get involved with, or the team back in Australia is there was a recent, sort of a few years ago now actually, the LIGO mission discovered a neutron star merger. So 2 neutron stars merged, generating a very sort of signature gravitational wave signature that LIGO was able to detect. And then everyone got Nobel Prizes. It was all very wonderful. I was very excited because it was the first direct detection of our process nucleosynthesis. So all the weird elements like platinum and iridium got synthesized in that event. And that's the first time we'd seen a place in our solar system that had occurred. Sorry, not solar system, universe that had occurred in. And so my colleagues in Australia ended up being on that paper that announced this neutron star merger with like a quarter of the astronomy community, which was fun. But anyway, back to the point of this talk is we want to be able to collect meteorites on the ground with their orbits intact, having imaged them using fireball camera networks to tie these meteorites to their parent asteroid. And thanks very much for listening. I would also like to sort of raise your awareness that if you're interested in the project and want to help yourself, you can sort of assist us. I mentioned that app that we developed. It's called Fireballs in the Sky. It's completely free. It's available for Android and iOS. It's a really nice star map, if anything. It also tells you where the next meteor shower is and where in the sky you should go look for it, as well as some of the news of the project and what various of our sort of colleagues are up to. But the kind of key thing about it is it's a really ideal way of reporting meteorites or fireballs that you see in the night sky. So if you're lucky enough to see a fireball event, you can use your smartphone to sort of point it at where the light came on, where you saw that light turn on, click, point it then at where the light turned off, click. That'll give you a nice render of your fireball. You can then tell us what color it was, how many seconds it lasted, did it break up, did you hear a sonic boom, all that kind of stuff. And if enough people see the same event, we can build in those observations into our network, into our observations made by our cameras to try and constrain the fireball itself, and if it dropped a meteorite and where that meteorite went. So the more observations we have, the better. So yeah, please encourage you to download this. It's completely free, and yeah, we love working with citizen scientists and bringing together as many observations as we can to find the first meteorite in the UK for 30 years. So with that, I'd like to thank you very much for having me, and would be more than happy to take any questions.
Right, thank you very much. That was brilliant. I really enjoyed that.
Yeah, that was very good.
Yeah.
Very good.
Thanks very much.
Yeah.
Full of enthusiasm. Did you get paid for it? Well,
Sorry.
I'd have done that for free. Oh, great.
Yeah. Yeah, I'm lucky to be paid to do this. I keep pinching myself that that's a thing
Yeah.
now.
Yeah. That's the best kind of job.
Exactly.
It's another illustration of what we seem to be seeing with digital cameras and processing nowadays. There's absolutely amazing amount of accuracy you can get into things that even 10 years ago it was just impossible.
Yeah, and it makes the life a lot easier. So there was an initial pilot network in Australia and in the Czech Republic and in Canada that used film cameras, and they were literally these monstrous, like, ton weight installations with like thousands of moving parts. Instead of having the digital shutter to cut your image up, you had a physical rotating filter with gaps in it to cut your image up. You had to like go there every month to go collect it. It took 7 people like a week to install one. Whereas the digital cameras, you can install one yourself in 2 hours. And the cost is like an order of magnitude less expensive. So yeah, we're very glad that digital technology has caught up with what film could do. And we can start replacing those older systems and bulkier systems.
Because presumably then you also had to examine every frame optically, but now I guess, I don't know, you didn't say, well, you can use AI to actually pinpoint these things as they happen, presumably.
Yeah, exactly. That's exactly what the team does basically now. The onboard computer on the camera goes through each image with an event detection that's like a machine learning AI, and just says, that's a satellite, that's a fireball, that's a bird bum, like, and we only get the interesting stuff.
Yeah, that's brilliant.
Have you ever had any reports of a fireball visible in daylight?
Yes, several times.
Good.
Yeah.
Oh, good. That's all right.
They do happen. They're rare because they have to be bright enough to cancel out the sun, but people do see them.
Yeah, I saw one about 40 years ago. That's aging me a bit, but it'd be the early 1980s. And yeah, I was driving down the dual carriageway near York, and this bright light just started at the top of the windscreen and just went down. I hadn't been an amateur astronomer. I thought I was hallucinating, but I thought it's just got to be. It can't be anything else but you know, a meteor, daylight meteor. But that's the only one I've ever seen. Amazing.
Yeah, they're really cool events when you see them. Yeah, I wasn't on the trip again because I was still banned, but my colleagues were searching through the desert and they were just walking along. And one of them, instead of looking up, looking down at the ground for meteorites, looked up and just happened to catch a daylight fireball go overhead. And it was like,
Wow.
What are the odds?
Exactly.
Brilliant.
What are the
Right.
odds?
Right.
Well, we should go look for that one, not
Never
this
seen
one.
one before us.
There was one in the Lake District about the same number of years ago, seen between Penrith and Keswick, and it had very bright colours and reds and things. And I was asked on Radio Cumbria what I thought it was. And to me, it was a bit of re-entering spacecraft because of the colours that you got from the metals, and it turned out to be that actually. Yeah, I can't remember the exact date, but it will be about 30 odd years ago. It could be the same one you saw at York. You know? Although it's the wrong direction for York. It looked to be travelling slowly across the sky, but it was very, very high and travelling very fast.
Yeah, space debris tends to be a lot slower than like meteorites or cometary fragments.
Yes.
So you can tell them they go a bit slower.
Because many years ago, it must have been in the, I think it was the early 90s, maybe before that, maybe the 80s. No, it would be the 90s, the early 90s. And I was at Braidwood at the Lanark Camera Club, which was there at that point, and it was dark at this area, and we were waiting on the guy with the key to come for the hall, and I happened to look up and I saw this massive explosion. It looked like an explosion, but it was a massive fireball, and I'm thinking, oh, is a plane actually exploded? It was. And I couldn't even say to anybody else because I was that stunned at what I had seen. And everybody else was just mingling around chatting. And I'm looking up because it was the first time I'd seen like a clear sky for weeks because it was a dark area. And I actually wrote to Sir Patrick Moore, and Patrick said it will be space debris into an atmosphere and things. I says, thank God it wasn't a plane, because even when I got home, I'm looking on the TV to see if there was any explosion, a plane crash or anything. But it was just so, it was quite frightening really to see, you know.
Yeah, particularly when like big bits of debris come in, they can look quite, spectacular.
Aye, because it was a massive fire. I mean, it was quite a good size across the sky, this thing, you know, and I'm thinking, what the hell is that, you know? Yeah. And I mean, earlier on this year, it was before lockdown and everything, I think it would be February, I saw a massive meteorite as well, looked like a fireball, was in the car, and we were coming into the Forth, and I happened to look out the front window, the windscreen, and I saw this thing, and it was there and then it wasn't there, and it was huge, this thing. And my pal, he was driving, and he didn't see it, and I didn't have anything to take a photograph with, and because I know I mentioned it to Julian about it on Facebook chat, but it was huge. I'd never seen anything as big as that before.
Wow. Yeah, no, they're super spectacular events.
Aye.
They're really cool to see.
Oh, I just couldn't stop talking about it.
Can I ask, you were talking about the iron meteorites being the remnants of the cores of extinct planets that have obviously been demolished by some kind of process. From previous generations of planetary formation, does that mean they existed before the present solar system existed, or they came from some other solar system, or where did they come from?
So our current idea is they come from our solar system. They look very much like a solar system object in terms of their chemistry. But basically, the way we think planets form, which is not a holistic model and by no means has consensus in the community, is you basically bash bigger and bigger stuff together. So you start with pebbles, you hit some pebbles together and they become a boulder, and then you hit some boulders together and they become, I don't know, a house-like thing. You bash a few of those together, and eventually you end up with what we call planetesimals. So they're very small planets that have differentiated, formed a core, formed a mantle, formed a crust, and you start smashing those together. So the Earth-Moon system, we think, was basically the final throes of that as a giant impact between a Mars-sized object and the proto-Earth, generating a really nice big core for us as those two cores merged and blowing out the crust itself to form the moon during that impact. So you would imagine that there would be potentially thousands of these small differentiated objects. Some of them survived and grew bigger and accumulated more planetesimals to form the planetary system that's stable now. Some of them got broken up, decimated by these large catastrophic impacts that disrupted the whole body. So yeah, they're as far as we know, they're all from our solar system. But yeah, just some of these smaller objects that no longer exist.
I know you can detect meteors by radio. Have you tried doing anything similar with Fireball?
I haven't personally, but I know lots of people do that. There's a load of people at NASA, I think, use radar as well to detect them. But yeah, and that's really nice because we lose the meteorite, meteoroid at that point, I guess, as soon as the light goes out. And we have to make some guesses based on the wind at the time, wind at different levels in the atmosphere, as well as how big or small it is. Whereas stuff like radio and radar can see the physical object in that dark flight path. So yeah, my colleagues are doing some work with the people working on from the radar and the radio side to do that.
It works when it's cloudy as well. That's the good thing.
Yes, yeah.
Another quick question. I know there's the Chang'e 5 mission. Is bringing back stuff. Is there any chance you'll ever get to see any of that?
I really hope so.
Are they likely to spread that around?
I mean, I think they're keen for, well, from a very brief conversation I had with one of their delegates at in a meeting in Sagamihara, when I was over there talking with the Japanese Space Agency's Hayabusa mission, they were saying, like, yeah, we want to talk about sort of like sharing the expertise, sharing the samples around with stuff that they can't do in-house. So yeah, I think a few of my colleagues are involved with negotiating with them to sort of like say, like, hey, we can do this particular analysis. Would you please give us some samples? So yeah, I'm not as involved with that mission as I am with Hayabusa 2, so I can't speak to it directly. But as far as I understand, I think the international community will get some.
Excellent.
Because yeah, that's again a super exciting mission. First sample return from the moon since Apollo, and from a really interesting place.
Yeah. That's very useful.
Can I? Will, do you want to ask a question?
Yep. Sorry, Will Joy. I'm actually a guest from the Edinburgh Astronomical Society, and so first time joining your group, but absolutely fantastic talk there, Luke. Absolutely wonderful. A couple of quick questions, actually. During your hunts for meteorites out in Australia, for example, when you're honing in on the ground, have you ever come across finding other meteorites, not ones which have dropped, simply from statistics? I've quite a lot of sort of experience of looking for meteorites myself, actually. And the second part of the question is, with your latest 3 grains of amazing cometary, not cometary, but asteroid debris, which you're going to get, how are you getting that? I mean, you know, it's got to be in a very contained way that's going to be kept away from the Earth's atmosphere and stuff like that. And what's the sort of implications of how you're going to analyze that to not contaminate it before you analyze it for yourself?
Looks like it.
That's a really good question. I'll speak to the first one first, and the answer is yes, we do find old meteorites in the outback of Australia. Again, I've been unlucky and never found one, but there's been some failed expeditions that still came back with 5 meteorites. They were just really old meteorites that had been there for maybe 1,000 years, and you could tell that they're all rusty. Some even had like moss growing on them, but still quite clearly not from the local area, and still quite clearly meteorites. So yeah, the team do bring back a lot of meteorites, but not the meteorite we were after. There's another group in Monash led by Andy Tompkins, who they go out every year just to search for the old ones. So they don't go after the ones we see; they go after just the ones that are there, and they bring back hundreds a year. So yeah, they do a really good job, because yeah, Australia is again one of those stable areas, has accumulated meteorites for thousands of years, and so they're just there on the surface. It's very stable, doesn't get rained on, they don't get weathered away as fast. As to the second question about the Hayabusa 2 grains, yeah, those grains give me nightmares already. They're going to be around the width of a human hair in size. So it's like, don't breathe in when you open the canister. If it's like what they sent us before, it's again an airtight container. They've drilled a little well where they put the tiny little, lift up with a tiny little needle, the tiny little grain, put it in the well, cover it over with glass, and then seal that with an inert atmosphere or a vacuum, so it's completely safe. We then get it at Glasgow, very carefully open it up in a clean lab. So there's no other dust around. So there's no chance of mistaking it for something else in the atmosphere. And then hold your nerve and desperately try and pick it up so it's on the end of a needle. So you can then take it into other analytical systems, again, under vacuum, and start taking images of it, figuring out what it's made of. I'm going to actually destroy a few of mine using a machine called an atom probe, where we dig out a little needle and tear it apart one atom at a time to figure out where those atoms were in the structure, what it's made of, and importantly, how much water's inside it. Because that's kind of one of the key questions we want to know is, like, this asteroid, we think is a water-rich asteroid. It's probably one of the most primitive asteroids in the solar system. And so, again, everything inside there formed in the first few million years of our solar system. So what was our solar system like before there were planets? And particularly interesting is, where was water? How was it distributed? How did it get to the Earth? So we want to know exactly how much is water's inside these. And we think the atom probe, we've done a test. We're pretty sure the atom probe can get us the water abundance.
That's fantastic. Thanks very much.
I came in rather late today. I'm sorry. This question may already have been answered, but I've read a lot in the past, because of global warming, about more and more meteorites being found on the polar ice, because they've been there, and as it melts, so these dark objects appear, and they've been picked up in some considerable quantity, I believe.
I'd not heard that, but I totally believe it. That makes complete sense to me. So yeah, that's really cool. I've often actually thought it might be worth looking at the terminal moraine of glaciers, where they just drop all their stuff, because if they've carried meteorites down from the major ice shelf, that's where they're going to drop all the space rocks.
There's a program on television about finding these, you know, on the polar ice. I can't remember whether it was. I think it's mainly the northern pole, polar ice, due to global warming.
Yeah. Oh, I totally believe that. Yeah, that's really cool. Can you send me that documentary?
I think, well, it's a few years ago, but I seem to remember seeing it on television. I didn't learn it anywhere else. Yeah, I couldn't tell you what it was. No.
Oh, cool.
It'll maybe be lurking somewhere on YouTube. You never know.
Yeah.
Aye.
Yeah. Well, I'm sure a Google search of meteorites, global warming, recovery.
You'll probably find something.
Oh, thanks for letting me know about that. I wasn't aware.
Any other questions?
Yes, can I ask a question about the cameras, please? Look, obviously a lot of these cameras in fairly remote places, judging by Australia and so on. Is there any data coming back real time, or do you have to go out and sort of comb through the results from all these hard disks?
So I guess there's two flavors of it. If they're attached to the internet, they can report back to us in real time if they've seen something. Yeah. But they don't. Otherwise, they don't communicate to us. So if I've seen a fireball, all my mate cameras have seen a fireball. Here's where you go look. Right. But every now and then we do have to go out there and physically get the hard drives, because they eventually fill up. And then we replace them with another set of the biggest hard drive that's on the market at a reasonable price at that time, and then take them back and put them in a supercomputer in Perth. And then they get reprocessed, because some of the cameras that are offline can then be rebooted into the system, and we can find a few more fireballs that we'd potentially missed.
Yeah. So they're kind of semi-autonomous. Presumably, if you spot one and one that's wired up to the internet, you can then go out and look at the other ones that were covering the same area. Is that how it works?
Yes. Yeah. Although to be able to contact them, they have to be attached to the internet. We can't, if they're completely autonomous, like have no Wi-Fi connection, then we can't talk to them. And so there's been a few fireballs where we thought there was a really good chance of a meteorite, but there was like a set of remote cameras that weren't online at the time, and we sent the expedition out first to go to those cameras, get that data back to refine our model before we went to search for it.
It's very hard work. And can I ask a second question that is following on from what Dr. Onions said about radar and so on? Obviously, the military and civil aviation sort of people must have lots of radar data. I don't know how secure it is or sensitive, but no way you can get them into your alliance, is there?
I mean, I don't see why. Well, I guess it depends on them. Like I know from other kind of agencies, like colleagues working with people in the States, that they're quite happy to share data, and because I think like there's the nuclear bomb detection system, but that picks up big fireballs. So so yeah, if anything explodes in the atmosphere or comes through the atmosphere at high velocities, this system picks it out, and they were able to triangulate fireballs and meteorites on the ground with that. So, and that was a collaboration I'm aware of. So yeah, I think it's just a question of introducing the right people to the right people, and that could totally happen. I for one, I'm just happy to work with everybody and anybody. So yeah.
If I can mention again, going back to Australia, I've got samples of meteorites that I use in talks, and of course I've got some tektite, and told that is moon splash found in the Australian desert. Can you expand any more on that?
Moon splash? Yeah,
from when, way back in the past, when a meteorite hit the moon, or some large object hit the moon, the molten material came flying off at such speeds that it left the moon's gravity, it was attracted by the Earth's gravity eventually, and landed, and found this stuff sort of in spray across the Australian desert. And it's like a glass, it's like a blue glass. Well, it's with a straw here.
Yeah, yeah.
And I mean, they considered it could be from the moon. I don't know if that has ever been considered.
So my understanding from tektites, from what I've read about, I haven't actually heard the lunar theory. My understanding from them is large asteroid impacts onto the Earth kick up a load of terrestrial, like Earth rock, melt it in the atmosphere, kick it out into space, and then it re-enters, generating those really cool kind of like molten droplet, teardrop. You can get the sort of like, they kind of look a bit like a disk or an alien spaceship, for want of a better shape description, as they kind of come into the atmosphere, or like the rings of Saturn around this like droplet in the middle. But yeah, so as far as my understanding of that field, which again is not one of my areas of expertise, our current paradigm is there bits of the Earth that have been blown out into space by giant impacts and then rained back down onto the Earth afterwards.
Definitely burnt on the outside, just as a meteorite would be. It's definitely burnt on the outside, just like a meteorite. And when you cut into it, it's a blue glassy.
Yeah. The whole thing's been molten at some point.
Yes.
Yep. Yeah, they're really cool objects. They're really. My colleague Anne-Marie at Glasgow is currently putting them in a CT scanner to see all the flow structures inside them, to try and figure out how they flew through the atmosphere, which is really kind of cool.
Can I go back to the thing about radar earlier on? I'm sure I heard in a previous CAS meeting about the fact that there's a lot of redundant military hardware lying about, radar hardware, which it wouldn't be very expensive to put to the use of tracking meteorites or asteroids heading earthward or that kind of thing. I don't know if that's anything you heard about.
Oh, yeah, you just got muted for the last bit there.
Sorry, I've just pressed. I'll let it go too soon. No, you people who are interested in meteors have ever pursued, where is this military hardware that we could get hold of at very reasonable cost and turn it to the skies instead of the Russians?
That's an interesting idea. Are you volunteering to install a radar system? Do you know someone who has military-grade radar systems?
It would certainly reduce my frustration every time I go out into the garden and see the clouds and I say I can't see anything.
I know how you feel, Klaus. Any other questions? No. Right. I'd like to thank Luke for that very interesting and informative talk. I thoroughly enjoyed it, and I think everyone else has enjoyed it as well. And from the comment I've had from someone on the chat, they said it has been a most enjoyable evening as well. So I'd like us to thank Luke in the usual way.
Thanks so much for having me. It's been a pleasure.
It's been brilliant.
Super.
Brilliant.
Thank you.
Yeah.